LP spaces. So far, we've seen Banach spaces, such as the continuous function on the interval AB, LP of n for p superior to 1. We have seen Hilbert spaces like R1, Cn, L2 of n. And we have seen also that any Cauchy sequences, so the sequences like Vk for k from 1 to infinity in V converges to some vector in the vector space. Okay, so this is a very important result to demonstrate that sequences converge. You just need to demonstrate that it's a Cauchy sequence. Okay, because a Cauchy sequence in every Banach space is convergent. So now we are dealing about the analysis of spaces of function. In particular, we are going to be interested in L1 of R, which is the set of function, okay, from R to C. So we take a real and give a complex number, such that the integral from minus infinity to plus infinity of the absolute value of f dx dx is bounded. Okay, so it's convergent. So the L is for Lebesgue. Lebesgue as the integral of Lebesgue. Okay, so how to check that the function belong to L for Lebesgue 1 of R? So the function that are integrable in that sense, in that meaning. Okay, so we can calculate the integral from minus infinity to plus infinity of the absolute value of f dx dx, or we can calculate the integral between minus 6 to f dx the f dt dt and see what happens. And see what if this has a limit when x goes to infinity. Then if this has a limit when x goes to infinity, then we can say that f belongs to L1 of R. So observation. For a function that take a real and give a complex number, the integral of minus infinity to plus infinity of the absolute value of f dx always makes sense. As a number, if f belong, of course, to L1 of R, because this integral is convergent, okay? If f belong to L1 of R by definition, then if f doesn't belong to f1 of R, this is going to infinity, so it's divergent. Okay, infinity. So this is infinity. EF does not belong to L1 of R. So we just calculate this quantity. If this quantity converge as a limit is bounded, so the function belongs to L1 of R. If not, F does not belong to L1 of R. So let's take some example. So, okay, if we want to take the integral from minus infinity of plus infinity of the absolute value of sinus x dx, clearly this integral goes to infinity. Indeed, I represent you absolute value of sinus x dx. Okay, so it's an infinite adding of r. Okay, so it clearly goes to infinity. And also, if we take the integral from minus infinity to plus infinity of the absolute value of exponential ix dx, it's also plus infinity. Okay, but the integral from minus infinity to plus infinity of the x dx does not necessarily make sense if f is a function from R to C. For example, if we take the integral of minus infinity or plus infinity of sinus x dx, okay, the integral of minus infinity or plus infinity exponential ix dx does not make sense. Okay, I remember now some very important inequalities that we are going to use and that are useful in the exercise on LP function. It's the order inequality. If we take P and Q, two numbers belonging to 1 plus infinity to this interval, such as the inverse of P plus the inverse of Q equals 1, then we've got this inequality. So what's the inequality? The inequality is the sum of the absolute module or absolute value of xk, yk, okay, varying from 0 to infinity, is always less than the product of two infinite sum. So the sum of the absolute value of xk at the power k at the power 1 of p, okay, for the first one, and multiply by the infinite sum from 0 to infinity, so of the absolute value of yk at the power of q at the wall at the power 1 in q. Okay, this is an important inequality for function. So now theorem, let's consider an interval I, which is an interval included in R, in the real numbers, and let's take two functions, f and g, let's call them f and g, to function from I to c. Okay, then we have also the inequality, the sum from 0 to infinity of the absolute value of xk plus yk at p power, the whole at the power 1 over p, is always less than the sum of two infinite series to infinite sum. First one is the sum from 0 to infinity of the absolute module of xk power p, the one at power 1 over p, and the second, the sum of the 0 plus infinity, the absolute value of yk at the power p, the power q, sorry, power 1 over q. Okay, so for p and q, such that, of course, 1 over p plus 1 over q equal to 1. If not, this inequality is not true. But for p and q, such that this inequality is true, we always have that the integral of an interval E included in R, that the absolute value of the product f of x by g of x dx, to integrate over the differentiate of x, is always less than two integral products. The first one is the integral over I of the absolute value of f x and power p dx per 1 over p, and the second one is the integral of I, the absolute value, the absolute module of g of ix per q, the one at power 1 over q. Okay, so for p equal to 1, we have this inequality also. We just have to change p to 1. Okay, so lemma, if the integral of the absolute value of f dx on an interval I is bounded, so it's less than infinity, so this integral is convergent, then the integral over this interval of the f dx is well defined, so it makes sense. And we have the following inequality: the absolute value of the integral of phi, the f of x dx, differentiate of x in the absolute value, is always less than the integral of phi of the absolute value of f dx dx. Okay, it's an important concept in spaces. So let's see now this concept. So it's a definition. So consider f a function from the real number to the complex. Okay, so by definition, the support of f is the set called support of f is the closure of the set of all the x belonging to R, such that f the x is different from 0. Okay, and we take the closure of that. This is the support of f. Second, f has a compact support if the support of f is bounded, which means that there always exist two real numbers, let's call them a and b, where the support of f is included in the segment from a to b included. So I just draw an example. So we took the example of this function f, and we clearly see that the support of f is clearly included in the lower limit a and the upper limit b. Okay, so this is the formal definition of the support of f, which is defined by using the closure of a set. Okay, so let's now take the continuous function over here. So by definition, the continuous function over here is the set of function from R to C such that f is continuous and f has a compact support. Okay, now let the continuous function over here is the set of function from R to C such that f is continuous and f of x goes to 0 when x goes to infinity. Okay, so the continuous function of R is the set of function continuous with the support compact. Okay, so let's give some example. Let's construct yes, a function. We call it key of I of x. Okay, key of I, because the interval of I is defined of the interval of I of x, which is equal to 1 if x belong to the interval y, and which is equal to 0 if x doesn't belong to the interval y. Okay, so I draw the function here, and we clearly see there is discontinuity. Okay, there is discontinuity at the lower bound of the interval e and the upper low of the interval e. Okay, let's not draw the function f of x, which is x power 3 minus x, which is x factor of x minus 1 factor of x plus 1. Okay, this is the function. And this function on R is not at support compact, okay, because it goes to infinity here, it goes to infinity here. But if we define an interval, we can say that the function is at support compact, you know, on the interval. Let's take other example. So f of x, which is x cubed minus x multiplied by the function key we just defined. Okay, x over the interval minus 1 to 1. Okay, so this is the function. I define it. This function is clearly at support contact over R. Okay, this, and for the fourth one is the same. We define, so f of x, x cubed minus x, key of the interval minus 1 half plus 1 half over x. Okay, we clearly see that this function, as I draw it, is at support compact. And on the contrary, if we take the function f of x is exponential minus 2 absolute value of x that I design here, it's not at support compact. The limit goes to 0 at plus or less infinity, but it's not at support compact. Okay, so let now consider the interval e, which is the interval a b, a not included and b neither. So let's consider the set of x belonging to R such that key of I of x different of 0 is the interval AB. Okay, so the support of key of I is the closure of the set of x belonging to R such as key I of I is different of 0, and I represent this support. Okay, so we have we clearly see by definition that the closure of the segment AB, A not included, B not included, is the segment AB with A and B included. So key of I as a compact support. Okay, and we can clearly see that the integral over R over the real number key of I of x dx, okay, is b minus a, and this is clearly bounded. This integral is convergent over R. If we take the integral here, I've not written, but it's from minus infinity to plus infinity, because we have only this portion that count in the integral. Okay, so this function belongs to L1 of R. Okay. Okay, f doesn't belong to the function of R. F doesn't belong to the continuous function of R because there is a discontinuity in A. We can see it, the discontinuity in B. The function goes to 0 when x goes to B by positive value, and goes to 1. Let's say it's 1 here when the function goes to B by negative value. So this function has discontinuity clearly. Okay, let's take another example. Let's say f of I of fx can be x cubed minus 6. Okay, so the set of x belonging to R, such as f is different of 0, is donc the union of different intervals. So I write the interval. Okay, because this function gets to 0 in 0, in 1, in minus 1. So this set is the minus infinity to minus 1 not included, union 1 to infinity, 1 not included clearly because in 1 the function is 0. Okay, f of 1 is 0. but we can also include -1 to 0, okay, and 0 not included, union 0 to 1, union 1 to infinity, okay. This is not the number, okay. So this is the set of function, this is the closure of the function. So the support of f, what's the support of f? Support of f is -infinity to +infinity, okay. So here there is no compact support. F doesn't belong to L1 of R, f doesn't belong to the continuous function at supercompact of R, f doesn't belong to the continuous function of R, because there is clearly a discontinuity, okay. Yeah, so let's take now f of x is x cubed minus x key of -1 1 of x. I draw this function. The support of f is the segment -1 1, which is compact. F belong to the compact function of R. F is continuous of R. There is no discontinuity, okay. So f belong to L1 of R, okay. So if we take, so f of x is x cubed minus x key of the interval -1 half 1 half x. F doesn't belong to C1 of R. F doesn't belong to C1 of R, but F belong to L1 of R, because F is integrable over the real. Okay, for the fifth example, that we take f of x is exponential -2 absolute value of x, which I draw the curvature of the function here. The support of f is the real numbers. There is no compact support. F does not belong to the continuous function at compact support in R. If f belong to the continuous function of R, f belong to L1 of R, yes. And the question is there a limit when x goes to infinity of the integral from -x to x, the exponential 1 to dt dt? This is the question. Okay, I'll recall you now this this fundamental stuff. Continuous function of 0 1, Banach space with respect to the norm. The infinite norm for f is defined as the sup of f of x for all the x describing the interval ab, okay. Here a will be 0 and b will be 1. So it's exactly the same argument. So the lemma is that the C0 of R is a Banach space with respect to the norm, with respect to the infinite norm, okay? So C0 of R is a Banach space with respect to the infinite norm of f, which is defined as the sup of absolute value of f dx for x describing R, okay? This is the infinite norm of f. And for this norm, the continuous function of R is a Banach space, okay? So another lemma, CC of R is a subspace of C0 of R, and therefore CC of R as the norm of f is the sup of the absolute value of f dx for x describing R, the real number, okay, the real line. But CC of R is not a Banach space. Indeed, in a Banach space, every Cauchy sequence, okay, the sequence of Vk for k from 1 to infinity, if Vk is a Cauchy sequence in V, converges to some V in V, okay, to some vector in the vector space. So proof of that, CC of R is a subset of C0 of R. Demo. Let's take two functions, f and g, that belong to CC of R. Let's take alpha, beta to scalar, to complex number, and let's form the function alpha f plus beta g. Okay, this is a function that belongs to C0 of R, and let's check if this belongs to the compact set CC of R. Okay, so I draw f, I draw g, and we see the intersection alpha f plus beta g here that belong to CC of R. So we have a compact support, and here and 0 after. Okay, so CC of R is a subspace of C0 of R. So now how to show that CC of R is not a Banach space? So it's in-house just to find one Cauchy sequence. So let's call it f of k for k from 0 to infinity in CC of R that does not converge to some function f that belong to CC of R. Why? Because in every Banach space, every Cauchy sequence is convergent. Okay, so if you find only one that does not converge, you demonstrate that you are not in a Banach space. Okay, let's interesting in the function f of x defined by sinus x of x for x different of 0 of f of x equal to 1 if x equal to 0. Okay, so this function that belong to C0 of R. I draw the function here. Okay, and let's define the function fk by fk of x is sinus x of over x if x belong to minus kp except 0. F of k of x equal to 1 if k equal to 0. Fk of x equal to 0 if x does not belong to the interval minus kp, it's a minus here that I forgot, minus kp. So f of x sinus x on x if x different of 0, and f of x is 1 if x equal to 0. So what's the lemma here? So the convergence sequence, all convergence sequences are Cauchy sequences. In a normal vector space, okay, if vk from curve from 0 to infinity is convergent, then vk from curve 0 to infinity or curve from 1 to infinity, that's not important where you start the sequence from, is Cauchy. Okay, so now we show that fk, clearly the fk, then I draw them, f1 in green, f2 in violet, f3 in dark. All the fk converge, okay, to f. Okay, so we can say that the infinite norm of the difference between f and fk goes to 0 when k goes to infinity. Okay, but in the absolute value of fk minus fx, okay, it's the same. If you take the absolute value of fk minus fx of fx minus fk is the same, okay, because we take the absolute value, is less than 1 over kp, kpi, whatever x real. Okay, so the infinite norm of the difference between f and fk, which is the sup, I remind you, for x describing here, of the absolute difference between fk and fx in x, is less than 1 over kp, and 1 over kp goes clearly to 0 when k goes to infinity. So the sequence of fk, curve from 1 to infinity, is a sequence that converge in the space C0 of R. Okay, so therefore it is also a Cauchy sequence according to the previous lemma, but fk belong to CC of R converge to f that belong to C0 of R, and f does not belong to CC of R. Okay, because f has clearly there is an infinite oscillation here. It's not a support a compact support. Okay, so fk belong to CC of R converge to f belonging to C0 f, but f does not belong to CC of R. Okay, so this is a Cauchy sequence, and this Cauchy sequence is not convergent in our space. This shows therefore that CC of R is not a Banach space, clearly, because in each Banach space every Cauchy sequence converge. So if we have just found a Cauchy sequence that does not converge for that space, so that space is not a Banach space. That's the way you demonstrate it. Okay. Yeah, let's take an application in physics. Yeah, a system in physics, in engineering, is often modeled as a black box with input-output. Okay, x of t is the input, the output is y of t, black box. There is a function, okay, k, from R to 2R, such as, yeah, this is the convolution, that's y of t is equal to the integral between minus infinity and plus infinity of k of st x s ds. Okay, this is for example, if we take y equal k of x, where k is the operator, kx of t is the integral between minus infinity and plus infinity of k st x s ds. Where is k well defined? This is the question. Okay, assume that k is bounded, so there exists a C strictly positive that where the the module or the absolute value of kst is less than c, whatever s and t, of course. Then the operator k is well defined for so x belong to C0 of R, clearly no. X belong to L1 of R. Okay, let's check it. So the integral from minus infinity to plus infinity of the absolute value of KSTXSDS is less than the integral because of the bound of K is bounded here of integral minus infinity of plus infinity of CXXSDS. C does not depend on the variable S of integration, so it can get out of the integral, the summation. So this is less than the integral that C multiplied by the integral from minus infinity to plus infinity of the absolute value of x's ds, and this is less than infinity. This is bounded. This is convergent. So then we can say that the integral between minus infinity and plus infinity of kst xs ds is well defined. Okay, so this is all for these lessons. I take many examples. So that's all for today for the LP spaces.